Greetings, AP Chem. Today we're going to be talking about two things, but because of the length of the video, it's going to actually be broken into two parts. But they're tied together, so we'll talk about them together, but just in two videos. So we're going to be talking about reaction quotients first, and then we're going to be talking about reaction quotients and how they tie together with this idea of something called Le Chatelier's principle. So first of all, we'll start talking about reaction quotients. What realistically a reaction quotient is it is a representation of the relative amounts of the products and reactants that you have at any given point in time. And that's the very technical definition of that. But what I think about it is kind of like, cue the cheesy sound effects. It's a snapshot of what your chemical reaction is doing at this point in time. So it is saying, hey, I have these reactants, these products, and what you do is you put them into a mathematical expression to check and see if you are close to equilibrium or not. It lets you know whether you need to make more reactant, more product, all that kind of stuff based on your current set of conditions. Because as a chemical reaction runs, you don't necessarily know if you've reached that equilibrium point at any point in time unless you can take a look at the concentrations and say, hey, I've reached equilibrium. We assume if it runs long enough, it does, but we can check by comparing our current conditions to what our equilibrium constant is and comparing the two of them. It is represented by a capital letter Q, not to be mistaken with the lowercase q of heat, so just be careful with that. And the calculation for the reaction quotient is literally identical to my equilibrium constant calculation that we did previously. So we're going to use this same equilibrium expression, products over reactants. The only difference is the numbers that we're putting in there, we don't know if they're at equilibrium, so that's why they're considered a quotient instead of just calculating our equilibrium constant. So there's not that big of a difference between them. And so what you're going to do is you're going to get a number, unitless, just like we would every other equilibrium constant calculation. But then with that unitless number, what you have to do is you need to compare that to your K, and then think about what that number means relative to your K value. So here's kind of how it works. If your Q is less than K, it means that you do not currently have enough products. And so your reaction is going to need to head in what we call the forward direction to make more products. If I go back here, remember, it's a ratio of products over reactants. So if I put in the numbers and I compare them and my number for the Q is too small, it means that I don't have enough in terms of quantity in my numerator, and I've got too much in my denominator because it's small. So if we do a comparison and our Q is less than our K, it means we don't have enough product and our reaction needs to proceed more heavily in the forward direction to get to equilibrium. If you hit a sweet spot where your Q is equal to K, it means bang, you're at equilibrium. Congrats, you get flowers and a parade and all that kind of stuff. It happens very rarely, so, you know, I guess take that with a grain of salt. And then lastly, if your Q value, so your current set of conditions, is greater than your K value, that means that you have too many products and that your reaction is going to need to head in the reverse reaction to get to equilibrium. It means you've got too many products on your numerator and not enough reactants in your denominator. And so we're going to make the numerator's concentration go down and the denominator's concentration go up when we head in the reverse direction. So it's kind of a mathematical conceptual idea at the same time. So you can look at true numbers. When we get into Le Chatelier's principle in our next video, you'll also see how that kind of ties together with how equilibrium shifts and can be adjusted in a different context. But right now we're going to start off with a pure problem, and that's it. So an equilibrium constant K is 2.4 times 10 to the third at a certain temperature for the reaction 2NO turns into N2 and O2. And we're going to assume that these are all gases because we know nitrogen and oxygen are gases unless we're doing this at like very close to absolute zero. So if a 1 liter flask contains 0.024 moles of NO, 2 moles of N2, and 2.6 moles of O2, Do more products or reactants need to be produced to reach equilibrium? So let us take a look at this problem. So when we start off doing an equilibrium reaction quotient calculation, the first thing you want to do, kind of just like all of these, is you're going to set up the equilibrium expression. And a lot of times on the AP exam, you literally get a point for just setting up the expression. So it is going to be products over reactants. So I have my concentration of N2 times my concentration of O2. Because we've got my two products here, I have coefficients of 1, so I have superscripts of 1 here in my equilibrium expression. And then it's going to be divided by the concentration of NO squared. So remember, this expression for my quotient is exactly the same as my equilibrium expression for any other type of process that we do. And then what we're going to do is we are going to put in our numbers into our concentrations here. Now this is a 1 liter flask, so we don't need to do any division. So my concentration of my N2 is going to be 2. Concentration of my O2 is 2.6. And I know, like I said, for some of you, it's going to bother you that you aren't putting in units here. You are just going to have to get over it. Okay. And then we're going to divide it by my concentration of the NO, and we're going to square that. So it's going to be 0.024 squared. Okay. So now we put this into our calculator and we get out a number. And when I do that, I got 9,027.8. Okay. So that's my current set of conditions. 9,027.8 when I put in my concentration of my products and my concentration, my products and my reactants. So when you look at this, we're going to compare this value here to our K value and see how that looks. So our K value is 2,400, or 2.4 times 10 to the third power. If you think about it, we always kind of eat the bigger one with our symbol here. So this is going to be greater than 2,400. So in this case, my Q is greater than my equilibrium constant. What that means mathematically is that I have too much stuff on top and not enough stuff on bottom. So what I need to do, remember this is product over reactant. So what I need to do is I need to make more reactant and then get rid of some product. So this stuff here that I have too much of needs to turn back into NO. Even though my equilibrium constant is big, it just means that right now I have too much stuff on my product side. So what's going to happen is I currently have too much product. Because, I think I spelled that right, let's see. Q is greater than K. So the reaction will favor the reverse reaction and make more reactant. Okay, so it says, do more products or reactants need to be produced? So I kind of explained that here. So I've got too much product, so the reaction will favor the reverse reaction and make more reactant. So what I've done here is I've talked about what's going to actually happen and then kind of the explanation for that. So if there's strictly a question about reaction quotient, then I think it's pretty easy to kind of figure out. What's going to happen, the bigger issue, is that we're going to probably apply this to something called Le Chatelier's principle. And Le Chatelier's principle deals with something that's at equilibrium and then we disturb it. And so what we'll be doing in our next video is taking a look at this Q concept and then applying it to all of these different scenarios and kind of seeing what happens there. So hopefully this kind of gives you a rough idea of what's going on with reaction quotient. And like I said, we will apply it to Le Chatelier's principle next. All right, we'll see you in just a minute. Hopefully, come back for it.